Hello and welcome. You are looking at a few example problems covering congruent triangles. Let's go straight to work here, and there will be 8 problems here that will be the exact same. Let's read the directions here. If the triangles cannot be proven congruent, circle not possible only, meaning leave the rest alone. If it's not possible, then we leave it be. If they can be proven congruent, circle congruent. Complete the congruent statement, state the reason they are congruent, like side angle side, and circle the isometry that maps one triangle to the other, meaning what kind of transformation takes place for one to be the other. So in order to do this, we're going to have to do a few things. Mostly, we have to look at what sides correspond to one another. Either you look at the image, like how the image appears, or you look at what sets are congruent. You look at if the things that are marked congruent is sufficient data, meaning if it's enough evidence for you to state that the entire triangles must be congruent to each other, then we'll go with that. And that will also help us with this part here, because if we write out what the statement is, then we'll know what kind of transformation took place. We know how reflections look compared to rotations and translations. So let's go ahead and decide. Now, not all of these will be marked congruent. I don't think. We'll have to take a look. Okay, here we have triangle ABC. Here's A. Here's a congruent angle that's with F. So if it is congruent, then A would be congruent to F, these parts. Segment AB would be congruent to segment FE, and angle B would be congruent to angle E. Now it looks like here we are going angle, side, angle here with angle, side, angle here. If that's the case, then it does appear that these are congruent. Angle, side, angle would be enough to say that triangle ABC is congruent to triangle FED in that exact order. If this said CBA, then this would say DEF. It's not always alphabetical, so just follow along what the other triangle says. In fact, it looks like all these might be ABC. Now, what was this? This looks like a rotation. To know the difference in all of them, translation, as you can probably see in number 2, translation happens when you're just, you're moving your image. Everything moves here, here, and here. There's no sort of flipping or anything else. You just took it and moved it. Reflection would kind of look like a mirror image. And I know some people sometimes confuse this for being mirror image, saying, hey, look, it reflected across this. Well, no, because if it was reflection, if you tilt your head, like I'm doing right now, if you tilt your head 45 degrees to the right, then your other triangle would be looking more like this right here. Boom, boom, boom. That's a reflection. Obviously not a very good drawing of that, but the rotation is if you took your computer screen or phone or whatever, flipped it over, and FED stands where ABC is right now. So that one is a rotation. Number 2, looks like you have angle, then angle, and side match with angle, angle, and side. This is sufficient information. Angle, angle, side is one of our congruency properties. In fact, let's write them out just so we have them listed here. There's side, angle, side, angle, side, angle, 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 side, 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 and HL. Those are the 5. If we get angle, side, side, or side, side, angle, or whatever you want to call it, that does not apply. So we'll take a look at that. Anyway, which triangle is this one? This is called triangle, let's see, ABC is here, so this is LMK. Also not alphabetical. This looks like a translation. I think we already mentioned that one. Okay, moving on down. Here we have triangle ABC, triangle ABC, and you have, looks like if this is ABC, this would be ADC. Now, I don't know that this is an angle bisector of any sort. I do know this becomes a segment bisector. In fact, it becomes a perpendicular bisector. Now, not everything is marked that we can mark. So once again, even though I don't know these 2 angles are congruent, I don't know these 2 angles are congruent, I also don't know these 2 segments are congruent. I do know these 2 segments are congruent. So far, that's all they really give you. The rest you have to deduce, such as this segment, AC, is shared in both triangles, means it's congruent to itself. And that's an important property. It's called the reflexive property. It's important because it is a set of sides that you need to say or know are congruent. Now, in a straight angle that adds to 180 degrees, if one is 90 degrees as a right angle, the other is 90 degrees as a right angle. And all right angles are congruent. So now that this image is marked up in such a way that you can now start to say, oh, do we have enough information? Here I have a side, angle, then side adjacent to it. Here I have side, angle, side adjacent to it that are marked congruent. Yeah, that's enough information. By the side, angle, side property, I can say that triangle ABC is congruent to triangle, what I say, ADC by the side, angle, side congruency. Now, what's really interesting about all of these things is you might ask, does it always have to be one of these? Yeah, sort of, or a combination of them, because these are the three transformations that produce isometries, meaning it makes something that's congruent to the other thing. Dilations don't. So if you think about what transformations are, or what isometries are, if you think about what congruent images are, it's if you can do a composition of transformations that can map one of your things on the other. So for instance, this one's a reflection, because I can reflect it across segment AC right here, or across this line that AC is on, and this would go over to here, and these points would be on each other right here. So that one is a reflection. Okay, number 4, let's see if there's enough information here. Well, here I have angle, side, side, 2 tick marks, 1 tick mark, angle, side, 2 tick marks, side, 1 tick mark, angle, side, side, let's just spell that naughty word out. That's not a good enough congruency conjecture. But the congruency property HL, standing for hypotenuse leg, is the one exception to this one, where if you have a right triangle, it actually is enough information to say that these two triangles are congruent. How can we know that for sure? Because what you could also do is you could use Pythagorean theorem and find out that this side's congruent to this side. You do c squared minus b squared equals a squared, c squared minus b squared equals a squared. And if c and b are equal to each other, then these a's have to be equal to each other. If you can find out these are congruent to each other, now you can get side, side, side with side, 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 or side, angle, side with side, angle, side. So what do? They say, instead of saving you a step or two, you can just say these are congruent now. They call it the HL property. If I have the hypotenuse is congruent, and if I have one pair of legs in each triangle, right triangle congruent, then you have enough. So these two triangles, ABC, is congruent to triangle, where we start, DEF. This one's actually alphabetical, by the HL property. Now this one's also a rotation. Again, you flip your computer screen 180 degrees, you will get a rotation out of it. Pretty sweet. Okay, 5, 6, 7, and 8, again, the same directions. So let's keep moving on with this. Okay, these are not congruence marks. These are marks of lines being parallel to each other. So I will, for a moment, draw a little extra to make sure that you can get the perception of what's actually parallel in this and where transversals are. If AB is parallel to CD, what you have here is a transversal. Well, you have 3 different transversals, but this is the only one that will be affecting in your actual 2 triangles that correspond to one another. Here I have 2 lines in a transversal, if you can see that. I might ask, where do you see sets of alternate interior angles within the triangles? Well, right here and right here. These 2 angles are actually congruent to each other because these 2 lines are parallel. Now, if I delete these, you can see where this was actually drawn to, but I'm going to keep that one because I'm going to set these and get these new sets of parallel lines. This one, let's draw it a little more parallel. This one and this one right here. Okay. Now when these 2 lines are parallel, where are now sets of alternate interior angles that are within your triangle? Because when these lines are parallel, alternate interior angles also are congruent. Right here and right here. Now if I remove all of these, I want you to now take a look at what is marked congruent. So now, look how much information we found out just by that alone. 2 sets of angles being congruent. Now there's nothing that says that these sides are congruent yet, it just says they're parallel. Parallel, parallel, parallel. Are there any sides we can mark congruent? Yeah, it looks like BC can be marked congruent to itself here. I can do a marking right there. That's reflexive property once again. So I want you to take a look at what these triangles are and how they're actually drawn here. In fact, I'm going to redraw triangle, like this triangle right here, BCD. I'm going to redraw it so it's facing the same way as ABC is. But now you need to see where your actual parts should be marked. So B is not going to be up here anymore. It looks like D, that obtuse angle, will be fitting up here. And C looks like it took place over here, and B is now down here. So if I mark this the same, where B, angle B looks like that, angle C looks like that, and BC, segment BC looks like that, I want you to just take a look at ABC with DCB. These are congruent. Now, what did I do to get this thing here? I rotated it 180 degrees. So unless you can see your markings, make sure that you mark them separately with how many marks, literally how many arc marks you have. Make sure that you can follow along with which triangle is supposed to be congruent here. Now, they are congruent. Triangle ABC is congruent to triangle DCB in terms of how they correspond. This is angle, side, angle. Now, that was a rotation again. Rotations here can make parallelograms. Reflections can make what are called kites. Maybe we will run into one here. Let's see. We will not run into one here. Okay. Here, once again, we do have parallel lines right here. AB and DE are parallel on number 6. Now, once again, this can act as a transversal for these two parallel lines, which can make this angle congruent to this angle because they are alternate interior angles. There's one set. Also, with these two parallel lines, this can also act as a transversal to make angle B congruent to angle D because they are also alternate interior angles. Finally, I have vertical angles right here. Check this out. Angle ACB, boom, 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 and angle DCE, boom, boom, boom. So those are also congruent. However, these are only parallel line marks. These are not congruent side marks. There's nothing that says these are congruent. Doesn't say something about C being the midpoint or AE bisecting DB, nothing like that. I have angle, angle, angle. Now, this is not enough information to say that these two triangles are congruent, actually. In fact, let me kind of show you why. Let's, well, technically, the reason why is because this is a dilation. One's a dilation of the other. What if I took this triangle here and cloned it, and I decided to enlarge it? But I enlarged it in such a way, well, I just enlarged it. But I do it in such a way that the angles are still congruent. Take a look. This angle is still congruent to this one. This angle is still congruent to this one. And this angle is still congruent to this one. All three angles are congruent, yet that's not enough I know these triangles aren't congruent. They are similar, which is a word you'll come across later in geometry, or you probably have at one point, but they're similar and proportional, but they are not congruent to one another. Angle, angle, angle is not enough information. Not possible, nothing else you have to say about this. You don't even have to say how they correspond, what kind of transformations they were. One of them could have been dilations. Okay, number 7. Here you have triangle ABC. Now look where things correspond here. When I said ABC, I never once ran across the single tick mark. So when I do M, because I'm going to start with that congruent angle, I'm not going to go across this way. I'm going to go across this way here. M, N, C with A, B, C. Okay, so let's see if these are congruent though. Do I have enough information? Well, not currently. There's nothing to say these lines are parallel here, but we do have vertical angles. Remember, we talked about that in just the last problem there. So now I do have angle, side angle with angle, side angle. It does look like MNC is congruent by angle, side angle. Now this one is not a rotation. Okay, it could have been a rotation. However, just kind of look at how you correspond parts here. This is a reflection across a line that would probably look about like that. A rotation, if this one would go this way, this one would go this way. So you see that would be a 180-degree rotation. So there's a difference there. This one's a reflection. Okay, last one here. I have angle of triangle ABC with it looks like what would correspond is DBC. Once again, reflection, boom, 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 boom. That's how they correspond. But what's marked congruent? These angles here. We could say this is congruent to itself, reflexive property. Question now, do I know these are right angles? No, I do not know these are right angles. I don't know that CB is perpendicular to AD. I also don't know that CB is a bisector AD. There's no hypotenuse leg thing going on here unless I know these were right triangles, and even if so, I would still need to know that the hypotenuses are congruent. These are the only parts that I can know are congruent. And angle blank side is not enough. We would need more information. This is not possible. These are not congruent. If they were congruent, it would be ABC's congruent to DBC, and it would be a reflection once again, but you still need another angle somewhere, it appears, or this angle and this set of sides, or something like that. You'd need more information. We do not have enough. Okay, number 9, triangle ABC is congruent to triangle DEF. Now they tell us this, that like this is what we need to find out here, and we need to support our claim with evidence. Now, this is on an actual graph, which means that we can figure out what the lengths are, and if we can find out using side angle side, or side side side, or angle side angle, or angle angle side, or HL, then we would have enough information. I'll go about this the easiest way possible, but I also will speak about different ways that you can go about it. First of all, if ABC is congruent to DEF, that means segment AB is congruent to segment DE, if so. So let's go ahead and count how far this goes. However far it goes, we can then do what? We can decide whether they're equal. So A, B, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, or do 6 minus negative 7. So AB is length 13. If DE is also length 13, then we're kind of good to go here. So let's see. Let's do 5 minus negative 8. That's 5 plus 8, which is 13. So DE also equals 13. So let's do this kind of as a 2-column proof. So I'll say AB is 13, DE is 13. You can kind of say it's given, right? So segment AB is congruent to segment DE. Okay, reason for that, equal lengths would mean congruent segments in this case. Okay, we could also do the same thing. AC 1, 3 would be congruent to DF 1, 3. So if that's the case, these would also be congruent. So let's see. Let's mark these two congruent here and here. AC 1, 2, 3, 4, 5. DF 1, 2, 3, 4, 5. So AC equals 5. DF equals 5. Also, given. Okay, and then AC is congruent to DF. Same reason as the other one. Segment AC is congruent to segment DF. Okay. That reason there. Equal lengths is same as congruent segments. Let's go and mark those congruent. Not last one, but what can we do from here? Looks like we would either want to get this angle in between or this side here, because we can use side, 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 or angle, side, angle, or side, angle, side, excuse me, and get that. So it's kind of your, pick your poison. Would you rather do distance formula, meaning essentially Pythagorean theorem? Here you have something length 5, something of length 13, and 5 and 13. So it's not too hard to do. Just use Pythagorean theorem from here. Unfortunately, you'll run across a decimal value. You can do that and figure out these side lengths actually would be congruent. But how come you know you can do Pythagorean theorem? I think that's a more important question. How do you know that this is a right angle right here? Okay. How do I say it? You can't say it's a right angle because it looks like it. Granted, it really does look like it. But what's more important about it looking like it is that it is one. How do we know? On a graph, you have right angles if your slopes are opposite reciprocals of each other. So that's the last one that I really want to do. Again, you can use Pythagorean theorem, but I want to prove more that this is actually a right triangle, that angle A is congruent to angle D because they're both right angles. So angle A is 90 degrees because the slope, here, let's do it this way. The slope of, what are we looking at? AC is undefined. It's something over 0. The slope of AB is 0 because it is flat. It's 0 over something. These are opposite reciprocals of each other. This is 0 divided by some number. This is some number divided by 0, or some change in that value at least. When you flip these, you get opposite reciprocals. That makes these right angles. Same with DF and ED. ED has an undefined slope because it's a vertical line, no change in x. DF is a slope of 0 because it has no change in y, and it's flat. So those are also opposite reciprocals of each other. So you could say angles A and D are right angles because they have opposite reciprocal slopes. Now they don't always have to be straight up and down, left and right. One could look like this, one could look like this, as long as these slopes are opposite reciprocals of each other. So mathematically, you could actually determine that. So 6, angle A is congruent to angle D because all right angles are congruent. Okay, and finally, we now have enough information to say that these two triangles are congruent to each other. Angle ABC and DEF, or triangle ABC, congruent to triangle DEF. With what congruency property here? Looks like side angle side with side angle side. Okay. Again, I could have done side, side, side. I could have done pretty much all of them. I could have probably figured out that these two slopes were the same. Probably more of a trigonometry thing to do, that these two angles were congruent, stuff like that. But I think that's enough there. You can show the evidence as a two-column proof? No, but you got more exposure to a two-column proof by looking at that, by looking at one. Number 10, complete a quadrilateral EFGH by finding coordinates for points G and H so that ABCD is congruent to EFGH. Okay, this one is a little bit more of the same thing, using graphs and such to figure out the rest. What we have to do is a couple things. I'm first going to draw EFGH in the same way as ABCD is currently drawn, meaning I want to make sure that I know what parts correspond. It won't be perfect, but well, you know what? In fact, let's make it perfect. I don't know if you'll be able to make it perfect on yours if you ever try something like this, but I want you to see it where I'm going with this. What's important is figuring out where points are supposed to go. Not just by transformation, like if this is a rotation or reflection or whatever, but also just by seeing how it actually flips. So if ABCD is congruent to EFGH, no, you can always do this. You can always draw things and say this is exactly how it would look if it was just translated over. If A is right there, E is right here. If B is right there, F is right here. If C is right here, G is right here. And if D is right here, H is right here. Now what I want to do next is take a look at and say, technically, what transformation takes place if I had to get EF to go exactly there? It looks like there's a 90-degree rotation counterclockwise. That's how E and F get where they are right there. Now, this thing is not drawn completely to scale, so I'm not saying, boom, here's your H, boom, here's your G, but this is the direction which they go. So what I want you to now think about is the fact that if E and F rotated 90 degrees counterclockwise, as slopes, what happens is whatever went up is now going left. Okay? So here's kind of like a legend, like a code that you can use. Whatever went up before is now going left. And trying to think about the up, left, whatever went left is now going down. Whatever went, so what I'm talking about is in terms of slopes. What I can figure out how much rise, how much run should go based on what's congruent. Whatever was going down is now going right. And whatever was going right is now going up. They're all rotating 90 degrees counterclockwise from where they were previously going. Now, you don't actually have to do a lot of work. I really only have to do this once, but EF is already drawn for you. Now, EF corresponded to AB. BC is where GF would now be once it's rotated this way. Okay, so BC does the following. To go from B to C, it goes up and to the right. It goes up 1, 2, 3, 4, 5, and to the right 1, 2, 3, 4, 5, 6, 7, 8. So when I try and find FG right here, instead of going up 5, I will go to the left 5. 1, 2, 3, 4, 5. Instead of going right 8, I will be going up 8. 1, 2, 3, 4, 5, 6, 7, 8. And here is where point G exists. After that rotation of 90 degrees, that's how much everything transformed. Okay? Hope that kind of makes sense. What you first have to do is figure out which things correspond, AB with EF, figure out what EF did to go from what AB was before, and you go from there. Now, I haven't yet found H. I could do something from E, but it's easier probably just to go from G to H, like from C to D. C to D goes down 1, 2, 3, 4. So instead of going down 4, I'm going to go to the right 4. 1, 2, 3, 4. Here's where H would sit. So if I now all I have to do is connect the dots. So if I fill them in, you'll now be looking at boom, 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 boom. There's E, F, G, H. Now they ask you to find the coordinates of G and H, not just draw them. G is at the point -3, 6, and H is at the point 1, 6. And there you are. There is the quadrilateral completion. Okay, number 11, find the values of T and R. All right, we have to use triangle angle sum theorem along with isosceles triangle theorem to try and get some of this stuff worked out. First of all, let's look at the bigger triangle because I actually have something given here. I can find out what this measure is because it's going to be the same as this measure, because in isosceles triangles, when segments are congruent, their respective opposite, or their angles opposite them, are also congruent to one another. So if this is some unknown x degrees, this is also some known x degrees. So x plus 48 equals 180 degrees. That's the triangle angle sum theorem. 2x plus 48 equals 180. 2x equals 132. So therefore x equals, what is that, 66? So x is 66 degrees, meaning this entire thing, 66, 66. So let's go ahead and replace those now. Okay. So how does that help us? Well, we have to still find out some more angles here. Let's go for, I said this one was given. This one's technically also given. This is 90 degrees. If this is 90 degrees, this is actually true for any isosceles right triangle. All isosceles right triangles have their other angles be 45 degrees each. Why? Well, think about it like this. If these are unknown angle, well, actually it's T. If these are unknown angle T's, T and T, T plus T, T plus T actually technically equals 90. I don't have to add the 90 here. In a right triangle, the other two angles are complementary to each other. So if they're complementary, then they are also equal. In this case, in an isosceles triangle. So T is 45. Okay, so T is 45 and 45. So what must R be? It has to be 66 minus 45, which is 21 degrees. So T is 45 degrees, R is 21 degrees. Not necessarily drawn to scale. There you are. Number 12, find the values of x and y. Okay, once again, isosceles triangle right here, this is 70, so if that's x, this is also x. So 2x plus 70 equals 180, 2x equals 110, therefore x equals 55 degrees. So 55 here, and 55 just inside here. This isn't, this part here is not 55. Okay, so let's start doing some other work here. If you might be looking at this massive triangle here, but I wouldn't look at that right there to start to make conclusions. I'd start to look at this little triangle right here. Here's an isosceles triangle. Okay. Now, this is not necessarily a right angle, so I wouldn't say because this is 55, this is therefore 35. No. Instead, I'd be looking more at the fact that this is an isosceles triangle, so if this is y, this is also y. Right? We don't know what it is yet. What we do know is this is a straight angle. So if this is 70 degrees here, this is 110 degrees here. Okay? This is also the exterior angle of this here, where you add up these two, you get 110. So 2y plus 110 is also 180 degrees. 2y is 70, so y is 35 degrees. Hey, look, it did end up being 35, but I'm just saying you couldn't, we don't know that for sure. If it's not marked as a right angle, don't be going off of that and just say that it is. Okay, so there's 35. And, boom, found x and y. Number 13, once again, some triangle stuffs here. I'd probably work inside the triangle first, find out what x is, because this one also has a y out here. You can't solve for 2 in just one equation. So let's add 58, 2x plus 12, and 3x minus 10, and we will get 180. Combine like terms, you can get 5x plus 70 minus 10 is plus 60 equals 180. 5x equals 120. And if I know my math, I believe that's 24. So x is 20, well, not 24 degrees, but x is 24. When you substitute that in here, this becomes, I guess, 60. And this becomes 62, I guess. Okay, 60 degrees, 62 degrees. So you can figure out this in a couple ways. It depends on how you'd like to do it. You could add these two, 58 and 60, and you'll get 118. That'll be equal to this. Or you could have done 180 minus 62, and you would have gotten 118. Either way, this equals 118. 2 times 24 is 48. So here's our equation. 48 plus y plus 20 equals 118. 48 plus 20 is 68. So y plus 68 equals 118. Subtract 68, y will equal 50. So there's x. There's y. Once again, it's just important to know your interior angle sums. Triangles are 180 degrees. Quadrilaterals are another 180. The interior angle sum is 180 times your number, 2 less than your number of sides. We talked about this once. It's equivalent to the number of triangles that exist in there. When you make them up, they're drawn from the interior angles. Anyway, I digress. Number of sides is n. D is the interior angle sum. For quadrilaterals, it's 360. Pentagons, it's 540. Hexagons, 720, etc. You practice them enough, you'll actually know them. Okay, complete the following proof by providing the missing statements or reasons. So we're going to be given some stuff, and we're going to prove this stuff, and part of it's filled out for us, which is pretty nice. You have some setup. You already know how many steps they're going to be. You just got to fill in the rest. EB is congruent to DB. Looks like that's given there, and that's actually already provided on here. Angle A and C are right angles. Okay, that's also given. They tell us that. We can fill that in. 3, a third given actually is this one here. B is the midpoint of AC. So far so good. Just getting the givens filled up. Okay, statement number 4. Definition of right angles. Well, what's true about definitions of right angles? All of them are equal to 90 degrees. Okay, that could be one thing we could say. I figure since they're already going to the triangle congruent statement here, and this one's regarding segments, maybe it's important to say that angle A is congruent to angle C at this point. Like when I said all right angles are congruent, that would be, I guess, the equivalent to saying here, angle A is congruent to angle C. You could say measure of angle A is equal to measure of angle C, which is equal to 90. That would also probably tell you that they're congruent. I'd rather go for the congruent statement here because it helps by, excuse me, it would help by looking at your markings here when we talk about what's congruent. Okay, definition of midpoint. Looks like we're going to start marking segments congruent. If B is the midpoint of AC, then segment AB is congruent to BC for that very reason. Definition of midpoint. So AB is congruent to segment BC for that reason. Triangle EAB, let's see, EAB is congruent to DCB. Looks like that's what corresponds. Okay, EAB, DCB. DCB. What reason would that be? Looks like we got angle, side, side working here. Angle, side, side. Well, we can't use that. But these are right triangles. That makes this a hypotenuse, and that makes this a leg, and this as well. We have hypotenuse, leg, congruent. This is enough information to say that this is HL. I'm just going to write HL. Now they want us to prove that angle E is congruent to angle D, these ones up here. How do I now know, because the rest of the triangle, because the entire triangle is congruent, I could actually mark the rest of this up. I could say, oh, yep, this, and that, and that. Why can we mark all these congruent? Well, now you know what parts correspond to each other, and because the triangles are congruent, their respective corresponding parts are congruent. This is something that we like to call CPCTC. Corresponding parts of congruent triangles are congruent. Therefore, angle A is congruent to angle D. If I want to make a short case about what CPCTC kind of really means, is what you want to do is build up enough evidence to provide a big picture idea to say the triangles are congruent. When you do, even if you couldn't prove something was congruent before, that means they must be congruent as a result. I think I made the murder analogy before, saying if you're pinpointing a guy for murder, but you didn't know that that guy was at the scene of the crime, but you build enough evidence to say the guy did murder the person, then you know that they were at the scene of the crime. Kind of iffy example, but it works for me. Okay, here's the last problem. Prove with a paragraph, flowchart, or two-column proof. You know what? No, let's do a flowchart proof. I'll still provide the reasons. I'll even number them for you, so you can lay it out as a two-column proof if you'd like. But I'm just going to go ahead and, give you a few bubble things to work with, etc. We're going to do flowchart proof because I want you to see where ideas connect, especially with one like this. Start with some givens here. Segment CR is congruent to segment AB. I'm just going to go ahead and write underneath what the reasons are. That one's given. Okay, that is from these tick marks here. The arrows indicate that they're parallel. So CR is parallel to AB as well. That is also given. Now in the end, we're going to prove the triangles are congruent, so it looks like we have to start to draw some more information here. Okay, this statement will not help me conclude anything else about the triangles, with the exception of this statement here. The way that flowchart proofs work are that you work from your given information to start drawing new conclusions. Maybe you can create new information as well, such as segment RB is congruent to itself by the reflexive property. Did we know that before? Well, because it's drawn, it's not given, but it's by the reflexive property. So the way flowchart proofs work are you draw from previous information if you can. If you can't, you create it as brand new. In other words, this will not connect to any of my other guys here in this flowchart here. If I number these, this was number 1, 2, I'm just going to call this one 3, reflexive property. I could have actually done something else before that, but I want you to see that so far nothing's connecting to anything else. Okay. Now, this parallel line one, though, does help you find something. And what does it help you find? Well, we talked about it in probably one of the first sets of problems here. When you have parallel lines, and if you have a transversal somewhere, you probably have sets of triangles where you can find alternate interior angles to be congruent, such as this angle, CRB, being congruent to this one right here, ABR. When these lines are parallel, these alternate interior angles are congruent. Now, these lines are not parallel. Therefore, I cannot say this angle is congruent to this one. But I can say these ones here. Now, this piece of information came from this right here. Because CR is parallel to AB, boom, I found this out. I found out that, what did we call it? Angle CR B is congruent to angle ABR. Why? Because alternate interior angles are congruent. I'll just put AIA. Okay. Now we have enough information here to prove that the triangles are congruent. Here we have a side, an angle, a side with side, angle, side. Side, angle, side, side, angle, side. Now I want to connect all three statements that had congruent markings to one final statement. Statement number 5 would say that by side, angle, side, triangle let's see, which one did they said CRB and ABR. Triangle CRB is congruent to triangle ABR. Now let's go ahead and connect the things that make that happen. Here's one of the sides with angle with side. So you see how this given statement, again, it didn't generate anything new. It didn't lead me to any conclusions except for the final one. This one I concluded all by myself, not because of any of these two things. This one came as a result of this statement being made. So that's how these things connect. So it's not as organized looking as a two-column proof, but it does help you connect better how you made previous statements. So maybe this one helps. And you can rewrite this one as a two-column proof very easily. These are the statements. These are the reasons below. And they're actually numbered. I even numbered them for you. So you could do that, and you have it good to go. And that's enough, and we have proved it. And that's it. Fiend.